Hello everyone. So in this video we are going to discuss a small number theory problem. So which says that 2 to the power n doesn't divide n factorial. Okay. So if you want to try it out, so do pause the video and do check out the solution later on. So talking about the idea of the proof, that is what we are going to do is like n factorial is also a natural number, so we can prime factorize it. So in the prime factorization, so the power of 2, if it is less than n, so then there's no question that 2 to the power n will be able to divide n factorial, right? So all we have to show is that the power of 2 in n factorial is less than n, right? So now for that you all must be knowing that there is a very famous formula for that, which is called the Legendre's formula. So yeah, we would be using that. So let's discuss a little bit about the formula, and then we will also try to generalize it. Okay, so try to generalize this result, but which is also a very trivial thing. So let's come to this first, that is 2 to the power n doesn't divide n factorial. So what we are going to do is we are going to figure out the highest power of or highest exponent of 2 present in n factorial. So what is n factorial? You are multiplying 1, 2, 3 till n. So now what we are doing is we are taking n by 2. So the greatest integer part of this number, then n by 2 square, the greatest integer part of this number, then n by 2 cube, and so on. Okay. Now you can very well understand that after a certain stage, as the power of 2 exceeds n, so all will be 0, the greatest integer part all will be 0. So now why does this formula work? So what's the argument for it? So an argument is like, so what you do is basically when you're doing n by 2, so you're basically checking from 1 to n how many numbers are divisible by 2. Okay, so from those numbers you basically extract 1, 2. Okay, 1, 2 from each of those numbers. Okay, so you have n by 2 this greatest integer function of n by 2, so those many 2's now you get. Okay, so now after getting these many 2's, now you notice that some of the numbers which only had 1, 2, like the number 6 and so on, so once you extracted 1, 2, so it doesn't have any more 2. But numbers like 4, 12, 8, so even after extracting 1, 2 from them, they still have more than 1, 2. So to get how many such numbers who have at least 2 2's in them, so basically we divide by 2 square. Okay, so that basically tells me how many multiples of 4 are there. So basically that tells me that how many numbers have at least 2 2's in them. So from them again I extract one more 2. So please note that already 2 was extracted when I did n by 2. So another 2 is being extracted. So now this time the numbers like 4 won't have any more 2's left in them. Okay, so they are exhausted. Now the numbers like 8. So I divide by 2 cube. Okay, n by 2 cube to figure out how many multiples of 8 are there. So or 2 cube are there. So that like from those numbers, now even after extracting 2 more 2's, I know that those numbers are having at least 3 2's. So I am going to extract one more 2. Okay, so I keep on doing this. Like if n is 100, so you can very well understand that 2 to the power 7 onwards, like so even if you just go with 2 to the power 7, so 100 by 2 to the power 7, so which is 128, so it's not going to work. Okay, because there are no multiples of 2 to the power 7 under 100. So from that stage onwards, all the greatest integer part is going to be 0. So that's how like it works, and even the same argument works for any prime number p. Okay, so you can use this for any prime like to figure out the highest exponent of any prime p under in n factorial. So now talking about this is the this sum. So this is an infinite sum. Again, after a certain stage all the terms are 0, so this sum gives me the exponent of 2 in n factorial. Now I can do some comparison. So I have n by 2 greatest integer part, so I know that this is less than or equals to n by 2. Okay, so and similarly like this is again less than or equals to n by 2 square, and so on, n by 2 cube. Now try to understand that after a certain time, like as I said, like the greatest integer part will be coming out to be 0, but still the numbers would be non-zero. Okay, so then we can basically say that this will be a strict inequality. Okay, so now I have this, that is, so this sum, and now this sum, if you look at it here, that is n, and if you take common, so it's half plus 1 by 2 square plus 1 by 2 cube. So it's an infinite GP series. Okay, so now what is the sum of this infinite GP series? That is, it's n times half over 1 by half, 1 minus half. so which is basically equals n times 1, and thus what we proved is that the power of whatever be the power of 2 in n, so it's strictly less than n, and that's why we are done. That is 2 to the power n doesn't divide n factorial. Now what about like any prime p? So if we try to generalize this statement, again it's a very trivial statement, because if it doesn't work for any if it doesn't work for 2, so obviously for higher numbers it won't work. Okay, so like if p is from 1 to n, so then p to the power n also doesn't divide, like here as you can see the statement, like 2 to the power n doesn't divide n factorial. So again the same thing, p to the power n doesn't divide n factorial. Now if p is greater than n, now where p is a prime, where p is a prime, now try to understand that if p is greater than n, so it doesn't make sense, because then p doesn't divide at all any number in n factorial. So now coming back to this, again the same logic, like if you can understand, if it doesn't happen with 2, it doesn't happen with p, but even if we similarly proceed as we did for 2, that is n by p greatest integer plus n by p square greatest integer and so on. So this is going to be less than n by p plus n by p square plus so on and so forth, and so this sum is nothing but n times 1 over p by 1 minus 1 by p. Okay, and that is basically n times as you can see, like 1 over p minus 1. Okay, now if p is like again greater than or equals to 2, so again like you can very well understand that this is again basically strictly like less than n if p is greater than 2. Okay, so and thus again the same logic works, and thus even for any prime also the same result holds. And yeah, if you enjoyed the video, so please don't forget to put a like, and thanks for watching, and keep watching and keep learning, and see you in the next one.